But just to show what it's good for, imagine a lot of stars falling together to form a nebula, a galaxy. As they come closer in, if they were very far out and moving slowly, so there was a little bit of area being generated, but on very long arms, distances from the center, then if the thing falls in, the distances to the center are shorter now. If all the stars are now close in, then these radii are smaller. And in order to sweep out the same area, they have to go a lot faster. So as the things come in, they swirl around, and thus we can roughly understand the qualitative shape of the spiral nebulae. You can also understand in the same way, exactly the same way a skater spins when you start with a leg out, moving slowly, and as you pull the leg in, it spins faster because when the leg is out, it's contributing, when it's moving slowly, a certain amount of area per second, and then when it comes in to get the same area, you have to go around faster. But I didn't prove it for the skater. The skater uses muscle force. Gravity is a different force, yet it's true for the skater. Now we have a problem. We can deduce often from one part of physics, like the law of gravitation, a principle, which turns out to be much more valid than the derivation. This doesn't happen in mathematics, that the theorems come out in places where they're not supposed to be. In other words, if we were to say that the postulates of physics were the law of gravitation, we could deduce the conservation of angular momentum, but only for gravitation. But we discover experimentally that the conservation of angular momentum is a much wider thing. Now, Newton had other postulates by which he could get the more general conservation law of angular momentum, but Newtonian laws were wrong. There's no forces, it's all a lot of baloney, the particles don't have orbits, and so on. Yet, the analog, the exact transformation of this principle about the areas, the conservation of angular momentum, is true with atomic motions in quantum mechanics and is still, as far as we can tell today, exact. So we have these wide principles which sweep across all the different laws, and if one takes too seriously his derivations and feels that this is only valid because this is valid, you cannot understand the interconnections of the different branches of physics. Someday, when physics is complete, then maybe with this kind of argument, we know all the laws, then we could start with some axioms, and no doubt somebody will figure out a particular way of doing it. And then all the deduction will be made. But while we don't know all the laws, we can use some to make guesses at theorems which extend beyond the proof. So in order to understand the physics, one must always have a neat balance and contain in his head all of the various propositions and their interrelationships, because the laws often extend beyond the range of their deductions. This will only have no importance when all the laws are known. Another thing that's interesting in the relation of mathematics to physics is this, a very strange thing, that by mathematical arguments you can show that you can start from very many different apparent starting points and come to the same thing. That's pretty clear. If you have axioms, you can use some of the theorems. But actually, in the physical laws are so delicately constructed that the statements of them have such qualitatively different character that it's very interesting. So if you'll permit me, I'm going to state the law of gravitation in 3 different ways, all of which are exactly equivalent, it turns out. But they sound completely different. 1, there's the forces between the objects as described before, and each object, when it sees the force on it, accelerates or changes its motion, rather, at a certain amount per second, as I've described before. The regular way, I call it Newton's law. Now there's a completely different way. That law says that the force depends on something at a finite distance away. See, it has what we call non-local quality. The force on this depends on where that one is over there. Now, you may not like the idea of action at a distance, but it can know what's going on over there. So then there's another way of stating the laws, which are very strange, and it's called the field way of representing the laws. And it's so very hard to explain, but I just want to give you some rough idea of what it's like. And it says, different thing, completely different thing, that there's a number at every point in space. I know it's a number. It's not a mechanism. It's the trouble with this whole physics, that it must be mathematical this way. There's a number at every point in space. Here's a number, here's a number, and so on. And the number's changing. It changes, rather, when you go from place to place. If an object is placed at one of these points, at somewhere in space, the force on it is in a direction in which that number